Okay, chapter 13, part 7. Uh, Topic is alternative structures. There are two different types of alternative structures that we're going to go over. The first one is called resonance, and in other videos, I'm going to take a look at what's called isomers. Now, quick definition: resonance is when you need more than one Lewis structure to show what's going on in a molecule. An isomer is when two or more molecules have the same exact formula, but actually two different Lewis structures. So they're kind of related. All right, so resonance. Your book mentions the compound benzene. And benzene, Lewis came out with his Lewis dot diagrams in the late 19th century. And I mentioned Kekula was the guy who did the dashes instead of dots for the bonds. Well, in the late 19th century, benzene was determined to have the formula C6H6. And people couldn't figure out what the structure was. And I don't know if it's legend or if it's actually true, but the legend is that Kekula awoke from a nightmare one night. He was dreaming about a snake eating his own tail, and that was the inspiration for him to come up with the structure of benzene. And he said that if you were to put the 6 carbon atoms in a hexagon and then connect one of the hydrogens to each carbon, and then alternated double bonds between the carbons, then that would satisfy the Lewis structure. And everybody said, oh, yeah, that's a great idea. However, in the 20th century, when they started looking at X-ray diffraction technology, what they found out is that wasn't the structure. Yes, the 6 carbon atoms were connected together in a ring, but what they had found through the X-ray technology is that the carbon-carbon single bond is long, and the carbon-carbon double bond, because of the pi bonding, is short. So if this was the correct structure for benzene, as you went around the hexagon, this bond would be really short, and then this one would be really long, and then this one would be short. You wouldn't come up with a regular hexagon. But what they found was it was a regular shaped hexagon, and the distances between the carbons were neither the correct distance for a single bond or the correct distance for a double bond. It was an average between the two. And it was almost as if there was a 1.5 bond that was created. Now, you can't have a 1.5 bond. Having 1.5 bond is like having 1.5 human beings. It just doesn't work, half a human being. What was happening here, they found out, is that when the carbons crowded together, it connected their electron charge clouds, and the molecule was able to hyperconjugate. It was able to spread the charge cloud out equally throughout the whole entire molecule. So what they constructed was this idea of resonance. They said, okay, here's what must be happening. We're going to draw another structure that is almost exactly like that, except for we're going to move the double bond to a different location. We redraw this with the hydrogens. And they said, well, what must be happening here is that since electrons move 80% of the speed of light, is that these two molecular structures must be interconverting at a really, really high speed to give you the blend which appears to be the average. And they called this back and forth switch between the conformations resonance. And the term has stuck, but it's actually a misnomer. What they found out is that it doesn't flip back and forth. There is no flipping back and forth. The structure really is the average of these two structures put together. In other words, you would need both of these diagrams, take the average of the two diagrams, and then that would give you the structure of benzene. Now, when the carbons crowd together, your book shows that the pi orbitals connect together. So a lot of times what they do is they draw benzene, this hexagon, to represent the benzene 6-carbon ring, and then they say, all right, all the electron clouds are connected, and they draw a little circle there to represent the connection of the pi orbitals. This is called a bond line structure, In organic chemistry, we care so little for the hydrogens that in bond line structure, we don't even draw the hydrogens. For instance, let's say we had a molecule, and I showed you this earlier in the year. If we had dodecane, and dodecane is C12H26. All the carbons are connected in a sequence, but the way they draw it is they say, all right, let's pretend there's a carbon with 3 hydrogens here, and then another carbon with 2 hydrogens, and then another carbon with 2 hydrogens, another carbon with 2 hydrogens. There's 4 carbons, 5, 6, 7, 8, 9, 10, 11, 12, and that would be the bond line structure for dodecane. And we would have a carbon here connected to 3 hydrogens, and then a carbon connected to 2, and then another carbon connected to 2. It's a lot easier to draw long structures like this using bond line. In fact, I'm not even going to have the patience to finish that off. All right, so what is resonance then? Resonance is really just hyperconjugation. It's when you need more than one diagram to show what's going on. So let's see what this looks like in your notes. They say benzene is cyclohexyl, which means it's a hexagon with carbons in it, with alternating double bonds between the carbons, and then that results in delocalized p orbitals. All right, so the pi bonds are connecting to each other and creating that ring of electron charge. That kind of gives us that distance of that 1.5 bond. Any system that has alternating double and single bonds is called a conjugated system, which means that it can hyperconjugate. It can spread out the charge over the structures that have the double and single bonds next to each other. Now, there are a lot of different types of resonance. Conjugated systems are only one type, but it's a very common type. In fact, in advanced biology, you would study a conjugated system called butadiene, which is what we call an isoprene unit, which you see in a lot of this alternating double single bond between the carbons. You see it in a lot of biological structures. So by definition, then, resonance is just going to be this. Anytime we need more than one structural formula to show what's going on in a molecule. But the only type that we're going to focus on at this level is the conjugated system, the alternating double and single bonds. Okay, so here is nitrate. Now, earlier in nitrate, I drew this structure right here, and I said, don't worry about where the double bond is. Well, the truth of the matter is, nitrogen, with the 3 bonds around it, it's not the length of a double bond to the oxygen and then 2 single bonds. It's really the length of a 1 1/3 bond, that the electronegative oxygens lend their charge cloud a little bit to the nitrogen, and then it spreads out evenly throughout the molecule to stabilize it. And we had talked about that in chapter 12 when we talked about mechanisms for polyatomic bonding. Now, in a resonance structure, a couple things I want to point out. First of all, the double arrows, these are the double arrows for resonance. The double arrows where you have an arrow going one way and the other way, that is for equilibria systems, which we'll study in the 4th Markin period. To go from one resonance structure to another, since you're only doing alternating double and single bonds, and if you really just want to go and move the double bond to each location, that's fine. But in advanced chemistry, the way you do resonance structures is for every bond you break, you create another one. In other words, in order to go from the first structure, I'll call this structure number 1, to structure number 2, I am going to take this double bond and I'm going to break it and move the electrons here. So you can see it in the second diagram. And then this pair of electrons, I'm going to move down here to create the double bond, which comes from the second structure. To go from structure number 2 to structure number 3, and I'll do that in blue, what we're going to do is we're going to take this electron pair and move it down and make the double bond. And then we're going to break this double bond and move the electron pair back here to go to diagram number 3. So you're not changing the way anything is connected. Nitrate is NO3 with a negative charge. That is the structure. And it is arranged with 3 equal bonds around the nitrogen, which makes it sp2 hybrid and makes it trigonal planar. Trigonal polar. Trigonal planar. And since it's trigonal planar and you have an oxygen on each nitrogen and they're all 1 1/3 bond, this is technically considered a nonpolar molecule. Okay, so try this one. Let's say we have carbonate, CO3 with a 2- charge. Go ahead and draw all 3 of the structures and give me, first of all, give me the resonance structures. Give me the geometry, the polarity, and the hybridization. That's funny. Hybridization on the central atom. And I will pause and wait for you. Okay, I waited long enough. Carbonate, going to do the same process. Start out with my valence electrons. Group 14 plus 3 times group 16 plus 2 electrons for the negative charge. So that gives me 24 electrons to work with. I'm going to put the electropositive element as the central, and I'm going to connect the 3 oxygens. That's going to use up 6 of my electrons. Now, that only leaves me with 18, but I need 18 just to complete the octets on the 3 oxygens, and then I would need 2 more. I'd need 20 to complete the octet on the carbon. So I'm going to try this with a double bond. And if I do that, this becomes 16 electrons, and that's all I need. I need 12 for the single bonded oxygens, and I need 4 more for the double bonded oxygen. And remember, this is a polyatomic ion, so we got to put brackets around the outside, and we got to put the -2 charge. Now for the structures, the resonance structures, we draw a double arrow, and then we draw our second structure, and you can just move that double bond around. Again, at an advanced level, like third year college or orgo, something of that nature, I would have you do electron pushing diagrams, and you would have to show me which bonds you broke and which bonds you formed. But at this level, we just want you to be aware of what resonance is and to be able to draw the structures. Not to justify the structures or to discuss the stability of the structures, which is something I would teach you in AP Chem. All right, so there's my 3 carbonate resonance structures. The organic stuff we're not going to have time for. I'm going to come back on the next video with saturated, unsaturated, and all that kind of stuff. We'll talk about that on the next video. So thank you very much.